So today we're going to learn about orbit, one of my favorite topics in physics. So we talked about this earlier in the year when we were doing two-dimensional kinematics. So imagine if I had a launcher that was positioned 5 meters off the ground, and I fired a projectile horizontally at 5 meters per second. Well, I chose 5 meters because if I use d equals 1/2 at squared, what I'm going to find is for this height, it's going to take exactly 1 second to hit the ground. This is traveling 5 meters per second. In the 1 second it takes to fall to the ground, it will end up traveling 5 meters horizontally and land a distance 5 meters away from the launcher. If I then put it back in and fire it twice as fast, I haven't changed the height. So it doesn't gain any extra time in the air. It just is traveling faster in that 1 second it takes to land. So it's going to travel 10 meters. We've done this before. It shouldn't be surprising then if I take it and double the speed again to 20 meters. It's still going to fall for 1 second. Now it's going to go 20 meters. Mr. Sampson, why are we going over this again? Because it occurred to Isaac Newton that if I fired it a little bit faster than that, okay, a lot faster than that, something interesting would happen because it turns out the world is not flat. The world happens to be a ball, right? And so it has a curvature to it. There's this horizon. And if I shoot this fast enough, it falls over the horizon and it basically misses the ground for a while. So if I shot it at 8,000 meters per second, and I chose this number carefully, in the 1 second it takes to fall to the ground, it travels 8,000 meters horizontally. And it turns out, given the curvature of the Earth, the ball would still be 1 meter in the air. It wouldn't have gotten any closer to the ground. Well, then it's never going to hit, is it? Provided it doesn't lose its any kinetic energy, it would never hit the ground. And when Newton realized this, he was like, "Oh my God, the moon is falling. It just doesn't hit the ground." And he drew this diagram, which is one of my favorite diagrams of all times. One of my life's dreams is to actually see a copy of this in his famous Principia Mathematica. I had a chance one time. Oh, I was in Pomona, California, and they had a library, and this book was out for research. Anyway, he drew this diagram. It's amazing. They sometimes call it Newton's Mountain. Okay, so he just shot the first shot. For some reason, he labeled D. It lands here. Shot E lands here. Shot F lands here. He didn't label the next one. I guess it shot G. Oh, there's is this G here, right? It hits the South Pole, and then he shoots the next one. And look what the next one does. It has a curvature that matches the curvature of the Earth, and it never lands. And he said, "Well, that's all astronomical objects are. They're just objects that have enough horizontal velocity that they just never hit the ground. They fall, but they keep missing the planet." So here's one way I have of conceptualizing that. It works for me. Maybe it'll work for you. So let's just say this is the International Space Station, and it's located at an altitude such that if it had no velocity at all, if I just like took the International Space Station straight up above the ground and let go of it with no horizontal velocity whatsoever. Remember, gravity does work in outer space. It would simply fall towards the ground. And let's just say it turns out at this altitude that it's at, if it was to fall to the center of the Earth, as long as the gravitational force continued to operate in the same way, it'd be different inside the Earth, but let's not worry about that. It would take 20 minutes to fall to here. But it's got so much horizontal velocity. In the 20 minutes it falls to here, it travels so far horizontally that it ends up over here and completely misses the Earth, ending up in this location. But now its velocity vector is pointing down our page. And in the 20 minutes it would take to fall from here to here, the International Space Station, instead of landing in the center of the Earth, is going to land so far over here that it actually missed again. And now its velocity is pointing to the left of my page. And in the 20 minutes it would take to fall to here, it's going to travel so far horizontally that it ends up over here. And it just keeps falling and missing and falling and missing. Now, a common misconception that people have, like I said, a lot of people have misconceptions about gravity. They think we go to space to put satellites in orbit because gravity is weaker there, and that maybe is something that makes satellites more able to do their job. But the truth is, you could have an object orbit the Earth, as long as it didn't hit any, basically as long as there wasn't any mountain in its way, it would be able to do it from any height. The only problem is on Earth we have air friction, and air friction is going to do negative work on the object and convert mechanical energy into thermal energy. So it's just going to fall to the ground. It's going to heat up and fall to the ground. It's going to lose kinetic energy. We go to space not to avoid gravity, but to avoid air friction, because if it's in space, it doesn't lose its kinetic energy. It maintains its ME, and it just continues to fall essentially forever. That's what the moon's been doing ever since it formed. Okay, so let's look at how we derive the formula for circular orbit. It's really not that hard, and it's really cool. Okay, so we're going to start off with Newton's law of universal gravitation. The force of gravity is equal to the mass of the satellite times the mass of the planet it's orbiting, divided by the square of the distance between the centers of the satellite and the planets it's orbiting, times this multiplier, the universal gravitational constant. But then we're also going to say, well, but you know what? It's going in a circular path, and that means we have a centripetal force. And centripetal force is always equal to the object that's traveling in a circular path times the square of the velocity of that object divided by the radius of its circular path. So I can then substitute this into this equation, getting this. So don't ask me why I flipped them around. That's kind of dumb of me. So basically, this is equal to this, and I get this set up. All right. Now I'm just going to clean it up. I'm going to say, well, okay, if I multiply by r, I could get rid of one of my r's. I get rid of all my little m's go away, right? And then I'm left with this, that I have the velocity of circular orbit is equal to the square root of gm over r. So if my velocity happens to equal the mass of the planet divided by the distance between the satellite and the center of the planet times the universal gravitational constant, take the square root, that object will be in circular orbit. It's really beautiful and pretty easy to derive. Now, here's the thing. You can derive it each time. You know what? It's a healthy and not hard thing to do, or you can simply memorize this one here. But you got to be careful if you get something wrong with memorizing and you get the wrong answer. But it's very easy to verify just, setting up the centripetal force with universal gravitation. Okay, so what we're saying then is if an object is projected horizontally at exactly this velocity, it will travel in a perfectly circular orbit, all right, with a larger mass at the center. Now, the reality is that almost never happens in the universe because, what are the odds that a randomly moving satellite is going to happen to have the perfect speed to go in a circular orbit? It almost never happens. In fact, when Johann Kepler came up with his laws of planetary motion, he made a flat out statement that said all planets orbit in elliptical orbits. He didn't know why, but now we do. It's not impossible for them to have circular orbits, it's just highly unlikely. There's probably some planet somewhere in the universe that has a perfectly circular orbit. Okay, so what if we projected this object with less velocity than what it takes? So if the orbital velocity was less than this value, what would happen? Well, you wouldn't make a perfect circle. You wouldn't end up as far away as you started. You'd end up falling a little bit closer to it. So I get this elliptical orbit where m is at the focus of. I have an ellipse, and m is at the far focus. What if I did the opposite? What if I sent it with a velocity that was faster than what it took for a circular orbit? Well, look what happens. It overshoots. So a circular orbit would go like this. I overshoot that. I go farther and farther and farther away. Eventually, gravity slows me down, turns me around, and brings me back. And once again, I have an ellipse. But in this case, the planet is at the near focus. All right. Uh, so orbits are usually elliptical because the orbital velocity is almost never exactly equal to this. But humans can make it exactly equal to this. But now, how fast could I project this? Like the faster I throw it, the farther and farther and farther it goes. And we say gravity extends to the infinite distance all the way across the universe. Well, not that the universe is infinite, but it goes as far as it can go. But the thing is, that doesn't mean it's strong enough to turn this object around and make it stop going away and bring it back towards the planet. There is a limit, and the limit is not that much. It turns out that if I project this object, if the velocity is greater than or equal to 2 gm over r, and we'll talk about this in a later screencast, then it never slows it down enough to make it stop going to the left and bring it around and make it come back to the right. It just goes and it goes and goes, and it's essentially escaped from this planet. It doesn't mean that this planet's gravity isn't pulling on the object. It means it's never going to be able to pull on it. This planet gets far enough away that this planet the force between them is insufficient to cause this object to turn around and come back. And we call that escape velocity. Now, one of the things I want you to learn about, one of the things College Board is going to quiz you about, is how energy, mechanical energy, plays out with orbits. So let's start with a simple situation, a perfectly circular orbit. If I have an object in a perfectly circular orbit, what that tells me, and that only happens when the orbital velocity is exactly equal to the square root gm over r. If that happens, since I'm going in a circle, this force is always perfectly centripetal, and that means then that the gravitational force vector is always completely perpendicular to the velocity vector of the object, and therefore it's doing zero work. So the kinetic energy of the object is never going to change because the force is always acting at a right angle to its motion. And so obviously in that case, the K would stay constant. It doesn't get any further or closer to the planet, so UG doesn't change, and unsurprisingly, ME doesn't change. But let's go back and examine those perpendicular orbits. Um, those elliptical orbits. I can't believe I just said perpendicular orbits. That's not much of an orbit, is it? Uh, if it would examine elliptical orbits. Okay, so now let's look at this one here. Let's just say I have an orbit such that the orbital velocity is either less than root gm over r, or more than root gm over r, but less than root 2 gm over r. So it is going to orbit. Okay. In that case, what we're going to find is sometimes gravity is doing positive work and sometimes gravity is doing negative work. And at 2 points in the path, it's doing zero work. So at this point here, it's perpendicular, it's doing zero work, right? But when this object gets to here, notice the velocity vector is this way, the force vector is this way. Since the force vector has a component that's opposite the direction of motion, it's going to do negative work, and this is going to lose kinetic energy. And it loses and loses and loses kinetic energy. The kinetic energy doesn't go all the way away, because otherwise it doesn't stop here, but it reaches a minimum. And at this point, at maximum distance, apogee, I think it's called, but don't quote me on that. At that point, what we have is at that one point, gravity is now perpendicular, does no work, but it quickly passes that, and now it's coming this way. And as it does, notice that it's moving this way. The gravitational force vector is this way. So there's definitely a component of the gravitational force vector that's acting in the direction of motion. So it's going to gain kinetic energy. And so when it gets to here, it's going to have its maximum kinetic energy. So again, it's when it's closest to the planet that it's orbiting, it's going to have its maximum kinetic energy. As it moves away from the planet, its kinetic energy gets smaller and smaller as gravity does negative work. It reaches its minimum kinetic energy at apogee. It picks up energy, and when it gets to, I believe it's called perigee, it once again has its maximum kinetic energy. Well, let's look at the ME of the system, shall we? So we said here, when I'm at perigee, at closest approach, I hope that's the word for it. I didn't look that one up. I should have done that. Okay. Uh, if I'm wrong, please inform me. And then I had to redo the screencast. Okay. It has maximum kinetic energy, but it's also the closest to the planet, so it has this minimum amount of UG. And if I sum those two, I get the mechanical energy of the system, just like I always do, right? Just like we did when we were studying energy in our previous units. Now, watch when it gets to here. Notice it's farther away. So it has gained UG, but in the process, it lost kinetic energy. And guess what? When I add those up, the ME hasn't changed. Why? Because there's no external work being done on the system. This is an internal force. It's like a tension force. It's internal, so it can't do work on the system. It can't change the energy of the system. It's not converting any energy to thermal energy. Uh, well, it does a little bit, but that's something we will look at later. Okay. So when it gets to here, at its furthest distance, kinetic energy is at a minimum, but the UG is at a maximum, and the ME of the system stays the same the whole time. College Board loves to ask about this. Unfortunately, it's not that hard to understand. This one, I doubt if they'll ask about it, but it's just too cool not to talk about. Communication satellites are really important. TV satellites, whatever. You want to be able to point a satellite at a spot in the sky and have that satellite always be in such a position that you can communicate with it. If it was constantly moving, it'd be kind of hard to do. So, like my son at the South Pole, they have satellites that are not in geosynchronous orbit, because geosynchronous orbit has to be above the equator of the planet. And so for him, there's certain times of the day when a satellite is passing over the South Pole. He can talk to us then, but otherwise he can't. So, but geosynchronous orbits are such that if you have a view of that part of the sky, it's never going to change in that part of the sky. How is that possible? It can't just sit in the sky. If it did, if it had no horizontal velocity, it had no orbital velocity, it would simply fall to the center of the Earth. So here's the deal: the way I have geosynchronous orbit, that means in time with the Earth. That means that the satellite's always going to be the same position in the sky, because uh, it stays over one part of the equator, because its orbital period, the amount of time it takes to orbit the planet, is exactly equal to the time it takes the Earth to orbit. So think about the satellite is doing this, but as it does, the world turns and keeps facing it, right? So the world is basically causing you to look at the satellite the whole time. So if I match the orbital period to the day length of the planet, the period of the planet's rotation, then it will always seem the same part of the sky. So for any given planetary mass, right, there's going to be exactly one height, one orbital distance r, where geosynchronous orbit is possible. And you better believe with Earth, it's pretty crowded up there. Everybody wants that little slice of the sky. Okay. So let's just see how this works. Okay. And this will be our last slide. And I know it's a lot, but it's so cool. So let's just talk about this. All right. So how fast does that satellite have to move in order to make it around in the same time that it takes the Earth's orbit? Well, here's what we'd say. Remember, velocity equals change in distance over time, change in position over time. So we're talking about a circular path, right? So in a circular path, the circumference of a circle is 2 pi r. Now I'm going to divide that by the time period t that it takes the planet to rotate on its axis. For Earth, 24 hours. Then I'm going to say, all right, well, so centripetal force is equal to v squared over r. And now I'm going to substitute the force for gravitational force. So I'm going to say m over r squared g equals centripetal force. My m's cancel out. We've done this before, Mr. Sampson. Yep. And so now I'm going. But what I'm going to do now is I'm going to say, okay, well, if I multiply by r and then move it over here, I end up getting gm equals v squared r. Now what I'm going to do is I'm going to take v and I'm going to substitute it for this, because I said this is the velocity you need to have, the speed you need to have in order to go around in that circle at that time. So I'm going to put that here, and then I'm going to square it. So I'm going to get 4 pi squared r squared over t squared times r. Well, I have r here, I have r here, so now I have r to the third power. And then I'm going to rearrange it so I can isolate the r third, r to the third power, and I'm going to basically take the cube root of it, and here you go. The height, or the distance between the center of the planet and the orbital altitude where geosynchronous orbit is possible is equal to the cube root of the gravitational constant times the mass of the planet times the square of the orbital period, in this case 24 hours squared. We had to turn it into seconds for this to work, divided by 4 pi squared. It's a beautiful thing. All right, so thank you for watching. I know this is a little bit long. See you in class tomorrow.